Good afternoon, we say currently here in Austria. Good morning or good evening, wherever you are on the planet joining our webinar on electric vehicles and circularity. So welcome everybody. My name is Gerfried Jungmeier. I am from Joanneum Research in Austria. Joanneum Research is a research organization doing applied research. And myself, I have a background as a mechanical engineer, but I'm active in the area of life cycle assessment since more than 30 years. I'm also your host and your moderator, and you're one of the speakers today. And I'm very happy that so many people are joining our webinar on the IEA Task 52, which deals with circularity and electric vehicles. Before we start, a few housekeeping rules. Please, all attendants, they are muted through the whole webinar. If you want to get in touch with us, especially, please post your questions on the presentations today in the chat. You have also the possibility to briefly introduce yourself in the chat when you ask a question, that we maybe know, or that we know your name, where you come from, and then please post your questions to the presenters in the chat window. You can do that already during the webinar, and then we have a special session on questions and answer. And finally, this event is recorded and will be made available afterwards. So all you hear and see today will be available online in a few weeks. This is the agenda for today. First, I give you a brief welcome. I already did. I give you a brief introduction also to the framework of this activity in the International Energy Agency on the Technology Collaboration Program. And then I give you a presentation on the definition and the assessment of circularity, of course, always in focus of electric vehicles. Afterwards, my German colleague, Jonas Peschke from the German Aerospace Centre will give his presentation on use cases for circularity with the example of a battery. Then we have a Q&A session, which will be moderated by our English colleague, Lorraine Hammond. She will manage the questions you put in the chat during the presentations. And finally, I will give you an outlook, what are the next steps, and a brief summary of today. I first want to introduce to you the Electric Vehicle Technology Collaboration Program of the International Energy Agency. It's a membership group collaborating under the framework of the IEA, and there are many of these different programs. The specific one on electric vehicle was formed in 1993 with the main activities that the members have to discuss their respective needs, share key information, and learn, of course, from the pool of electric vehicle experience around the globe. So this is just one small puzzle, this webinar today, which fulfills at least this information exchange and to exchange and deepen the knowledge on electric vehicles. So far, we are 18 member countries. You see here on the list, so at least we are relatively well spread over the globe. So we have many different perspectives from the different countries, and this collaboration framework gives us the possibility to exchange. The work of this technology collaboration program is organized in different tasks that are always focused on a very specific research topic, for example, on electric freight vehicle, on marine applications, on critical materials, on battery swapping, and any others. So there's a broad, long list of different task activities ongoing. And this webinar today is focusing on one of these tasks. It's a task 52 on electric vehicles and circularity. And you will see what our task is doing. What is the goal of our task 52? It started on the beginning of this year and it will run in total for 3 years. And the main idea is really to analyze, discuss, and document the main challenges and opportunities for electric vehicle and the different components to reach circularity, to reach at least a higher degree of circularity. At least we are going to identify and analyze different possibilities to further increase the circularity of electric vehicles. And one key element is, of course, always the exchange with the different stakeholders from industry, government, and research to address decision makers with the things we do and with recommendations we're ending up. At least our work is split in two main areas. One area is the assessment of circularity, and this activity is led by Joanneum Research. Also, the first presentation will be dedicated to this aspect. And the second key area is industrial use cases for circularity, because we always need industry on board to address them and see how in real industrial environment, circularity can be improved. Just to give you on the very beginning a small taste of what we do when we talk about circularity, we are a technology collaboration program, so we do many technical analysis. And in the area of circularity, we want to address circularity issues of different vehicles. For example, of a conventional combustion engine vehicle using petrol and a battery electric vehicle using renewable electricity. One, providing only transportation services. Secondly, also providing transportation services and vehicle-to-grid services. In our assessment, we first start with a mass balance. So we count all the masses that are involved in the lifetime of these three vehicles, and then we get an absolute amount of mass that is involved to provide the transportation service. In the next step, we have developed an approach to make an impact assessment to assess the circularity potential, to identify which of these masses are circular and which of these masses are non-circular. And combining this information, we end up with a result giving you the mass per driven kilometer of a vehicle driving 200,000 kilometers in gram per kilometer. And you see the red part is the not circular mass in the life cycle, and the green part is the circular mass. This is just a first appetizer for you to join us the whole webinar, and what is the background of this methodology and how we come to this results I'll show you later on. Who are we? Yeah, we are in this task. We have 9 countries on board. So you see the 9 countries here. We count Europe, the European Commission, as one country, at least because the European Commission is joining also as a country the technology collaboration programs. And in these 9 countries, we have 10 partners, at least spread all over, more or less all over the globe. So we are really a quite international team dealing with circularity and electric vehicle. I have the pleasure to be the Austrian task manager, and I also got a funding from our national government that we are able to manage and organize this task. As I've mentioned before, this task is split in 2 different areas. One is about the assessment of circularity, to give a definition what is circularity, to see what's going on in the different countries when they work on their circularity strategies, to also see what these 10R principles of circularity means. I will later on explain what R stands for. And then, of course, to see how we can really assess circularity, how can we measure circularity, and how can we really apply it to different vehicles, to different components, and that we do in different case studies. The second area, which is led by the German Aerospace Centre, is about industrial use cases of circularity. Starting with these 10R principles of circularity, we are zooming in initial use cases. One of these use cases on battery you will also hear about today. The next one is about e-motors, and the next one will be about structural components, and maybe there will be further use cases we have not yet identified. In that area too, we have workshops to interact with the different stakeholders to see where are we today and what do we need to further develop circularity, to make these vehicles more circular, what are the opportunities, but also to see what are the barriers or the threats. So this is about our task in general, what we plan here. And now I'm presenting our current finding we have developed during this year. It's about the definition and the assessment on circularity. On the very beginning, we started with an assessment of national circularity strategies. In total, we have analyzed 22 countries, at least the countries joining the technology collaboration program, but also additional countries that are somehow of interest for this group. And we looked if a country has a circular economy strategy, at least how do they define circular economy? Are principles of circularity included in the strategy, which are addressed, and what are the key sectors especially addressed? Are there any national goals in reaching a higher degree of circularity? What are the different indicators? And of course, our specific interest is there something in this national circularity strategies specifically addressing vehicles or batteries, and especially renewable energy systems like photovoltaic or wind and etc. So this was at least the starting point of assessing these national circularity strategies. So what did we find? We started first to see these 10 R principles of circular economy, how much are they used in the national circularity strategies. And you see here on the left-hand side, the numbers, how many countries mention these R principles. And now I open the secret here. What does R mean? R means refuse, repurpose, remanufacture, refurbish, recover, rethink, repair, reduce, reuse, and recycle. So these are at least 10 different possibilities to increase circularity on total different technical levels within the different supply chains, but these at least are the key principles that are used in circularity strategies. And what we see here is that at least 5 of them, rethink, repair, reduce, reuse, and recycle, are very often used. So at least 18 national strategies we have analyzed, and 16 countries at least use these 5 principles, whereas the others, refuse, repurpose, are not so much addressed in the different circularity strategies. And on the right-hand side, we looked what are the key sectors addressed here. And one of the key sectors is really the construction and the building sector, because the total amounts of material coming out of this sector is most probably the biggest fraction. Then plastic is addressed, food, water, nutrients, and so on. And battery and vehicles is only mentioned in 8 of these 18 national strategies, somehow explicitly address some circularity issues related to batteries and vehicles. And secondly, which was a very interesting exercise, is do we find a definition of circular economy in these different national strategies that is somehow similar from one country to the other one? And to be honest, we did not find one unique definition of circularity. What we found is that different aspects are addressed in the different strategies. Some address more economic aspects, some address more social aspects, raw material or environmental aspects. And at least you see here from the wording here, sustainability, very general, up to just reducing greenhouse gases and reduce waste. Life cycle of products is extended. So all the different wordings here you find here, but there is so far no common term. What is a circular economy really? So from our analysis of these strategies, we found out that 18 countries have a national strategy on circularity. We've analyzed 22 countries. We've also seen that the 10R principles are addressed by most of these strategies. The key sectors are identified in the strategies, but there is no common and unique definition. At least there's a very broad, sometimes very generic description of circularity, and different aspects like in sustainability, environmental, economic, and social aspects are covered. So this was the first part of our exercise. So we said, that is difficult. So we need at least to think about what do we describe as circularity, especially when we look on electric vehicles and the overall system we need to provide a transportation service. So it's a little bit an idea that we thought we need in the overall lifetime of a vehicle to address circularity. And if you look at this at least quite famous graph on a circular economy, we said, okay, there's a certain amount of mass that is somehow going in circle because it's secondary material when you do something and it's recycled or reused or refurbished on the end of life. But at least there's a total mass because there's still virgin material going in and there's still waste and emissions coming out. But this was our initial idea because we thought that circularity somehow has to do something with mass. Yeah? So at least mass and material is going in, mass and material is coming out, and the transportation service is provided. So our initial approach was very simple, saying, okay, we can maybe measure circularity as a percentage of the circular mass in relation to the total mass. Yeah? And this can be between 0 and 100%. And we know from life cycle assessment how much mass you need for a transportation service, of course. So this was the starting point, saying, okay, circularity in our thinking has something to do with mass. Some of the mass is going in a circle and some of the mass is lost, and the relation between them is a percentage. In the next step, we started to find a definition from the perspective of life cycle assessment. So we have we're a little bit biased maybe also in that task, especially in this area one. I'm talking now about what is biased. We use LCA, we use the overall life cycle thinking. And what we think is 100% circular system is, if you look on the graph here, on one hand, we have 100% closed material cycle. We use recycling material, we recover the energy, we repair, we reuse, we redesign, we remanufacture. So all the material physically is in a closed cycle. And of course, this cycle is driven or powered by renewable energy, because fossil energy is not circular. And of course, this material in combination with renewable energy provide you transportation services to satisfy a given mobility demand. And this is the shortest version of our description of circularity: closed material cycle, renewable energy, providing a service or a product. And with this system, we are aware that this is a very visionary definition. But if you really fulfill this, then we say we are 100% circular, and everything less than 100% is towards circularity. Because we have a visionary target, it's a long-term target, we are aware of that, but it's not necessary already today to reach 100% circularity. It's more a question if our new product, especially our electric vehicles and the power system behind that, is at least going towards more circularity. And with this approach, with this definition, we think we have a possibility to measure circularity with the circularity potential, as we call it, to see if a new system is hopefully more circular than an existing system. So using this definition, in our next step, we developed a methodology. Can we assess the circularity potential? And we started in our assessment using the work done since many years by the Ellen MacArthur Foundation. They have developed the Material Circularity Index, which is split in two parts. One is really material specific for steel, for aluminium, for copper, describing the material, how much secondary material is in a new product or how much can be recycled on the end of life. And secondly, this material circularity index also has a utility factor, because if you use a ton of steel in a car, in a passenger car, it's maybe less circular compared if you use a ton of steel in a public bus, because in the public bus, normally you provide much more transportation service in the lifetime with this ton of steel compared to a passenger car. So this utility factor gives you information how intensive the material is used, and this combination of these two factors is the so-called material circularity index. This was a starting point. The next step, we thought we need to calculate the circularity potential, and we started at least saying, okay, if circularity has something to do with mass, we need a mass balance. So first we apply a dynamic life cycle methodology to identify the mass flows in the system, in the production of the system, in the operation of the system, and in the end of life. So at least we cover here the overall life cycle of the vehicles. In the next step, we have normalized the material circularity index to 0%. The Ellen MacArthur Foundation has a 10% for circular, because they also have included systems that are less circular than a compared system. We normalize this. In the next step, we have also been aware that in the mass balance, for systems that use energy, and all of these systems, they need energy, we also have to include the primary energy, especially the fossil energy, because the fossil energy, oil, gas, and coal, has also a mass. You need, for example, to drive a car, conventional car, you need oil to make diesel or gasoline. So we also included the primary energy demand. And then we have a full mass balance of a component of an overall vehicle that you need in the overall lifetime. And then in our impact assessment, we have the possibilities to identify which of these mass flows are circular and which are non-circular. I show you on the next slide. And if we have identified this, then we can calculate the total mass, for example, per driven kilometer or per component. We can also sort out what are critical raw materials and maybe non-critical materials, for example, the antimony equivalent, quite well known to LCA experts. And we can also distinguish between renewable and non-renewable materials. So finally, we end up with the circularity potential, which is between 0% and 100%. And so this is more or less the initial approach we have developed in our task. And the most tricky thing is, of course, the assessment. When you once put the mass balance of your transportation system, you see here in the middle, the overall transportation system of an electric car, and you need inputs and you need outputs during the whole life cycle. The red ones are the non-circular flows, the non-circular input flows, for example, non-renewable virgin material, non-renewable energy, but also non-circular outflows like waste, losses, releases, and non-recoverable components. And the other one are really the circular inflows, like renewable material, renewable energy, recycled material, reused components, and also, there are outflows, recycled materials, components for reuse, recovered renewable energy, and some biological effects, composting is also included here. And the circular flows, the green flows, they are in a circle. They can be used again for the same system. So you can maybe use the secondary material to make a new vehicle, but we can say also you can look on other systems. So as long as we can use the secondary material for any other further product, we still say this is circular flow. This means these other systems on the very bottom of this page. Yeah? So this is the tricky thing to identify in the mass balance, what is the circular mass and what is the non-circular mass. Having said that, we have now to test if this kind of assessment really could work in reality. And for that, we had a good opportunity here in Austria, because we have an Austrian industry partner who has developed a component for an electric vehicle made from different materials. And he made the same component with the same lifetime, the same characteristics. Once the main material is aluminium, steel, carbon fiber plastics, wood. And for wood, we look different end-of-life scenario, recycling and energy recovery. We use life cycle assessment using the material circularity index, and we got all the data of this component. So these components, I've seen them, I've touched them, so they really exist, these 4 components made from different materials. And we wanted to test if our circularity assessment gives additional information. So we looked on different indicators on greenhouse gases, primary energy, but a strong focus on indicators for circularity, like the total material, the non-circular material, the recycled content, and at least also the circularity potential. So we applied this methodology to this specific electric vehicle component. We started with the weight of the different components, and you see here now always these 5 bars for aluminium, steel, plastic, wood for the different recycling and energy recover possibilities. So this is really the weight of the component. And we've also checked that the weight does not influence the energy consumption during lifetime significantly. So the weight difference, finally in the modeling, we found out it's not so relevant. But this is the original weight of this vehicle component. And already from the weight, we can learn something about circularity. Because if you look on the weight, so this is again the same bars showing the weight. On the left-hand side, on the production side, and on the right-hand side, on the end-of-life side. And we wanted to see already on the component, which is circular material in there. So how much recycled material on the production side? How much virgin renewable material, in our case, it's wood, is already included in the component and is at least circular. And of course, in the end of life, if we generate energy from the wood, of course, to make renewable energy recovery. So here you see the red ones is the non-circular mass already when you look at the component, and the green one is already the part that is circular. And you see here there's a difference, of course, for the different materials. In the production phase, we have, of course, secondary steel, secondary aluminium, but we have also here virgin renewable material. In the end of life phase, the amount of circular, the share is bigger because the recycling of steel and aluminium, of course, is higher in the end of life phase compared to the secondary material input on the production side. I've mentioned before, very important for this circularity assessment in our view is also to look on the fossil primary energy. So in life cycle assessment, we have this cumulated energy demand. So we know how many kilowatt hour per component you need to make the component. And it's very easy to convert the kilowatt hour of energy into mass. And that happens in the next step when we convert the primary energy with a heating value and put the additional weight of the primary energy in the total mass balance, which you see here on the right-hand side. So this is the total mass, the mass of the component, plus all the fossil energy at least you need to make the component. So you get at least the total mass that is involved. And you see here that even if the carbon fiber component has the lowest weight, the production of the carbon fiber is very energy intensive. So at least the primary energy demand in a mass balance is very much higher for the plastic component compared, for example, to the wood component. So at least we have here the total mass balance. And then we need to calculate the circularity potential. So we first look on the material circularity index or indicator of the different materials. We calculate them according to the Ellen MacArthur Foundation. We split it in the production and in the end of life phase, and we have normalized it. And depending on the different materials you're looking here, the material circularity is between 0%, which is at least 100% linear, so not circular, and some of these go up to 40, 50, or even 60% in this indicator. And the final step is now really to make this impact assessment, identify the circular and the non-circular flows in the overall life cycle. Then we end up with the circularity potential, which is a value between 0 and 100%. In that case, the steel has the highest circularity potential compared the carbon fiber plastic component has the lowest circularity potential, which only is a 3%, and the aluminium and the wood is just in between. And using this information from the circularity potential, from the impact assessment, we can calculate in the final step saying, okay, what is the total mass involved in our system, and what is the circular material, which is the green part, and the non-circular material is the red part. And finally, of course, we need to look on two criteria to optimize in future. On one hand, to minimize the total amount of material, of course, because the lower amount of mass you need for the same functionality, the more circular you are. And secondly, of course, we need a high share of this green part of the circular material. So the higher the circularity potential, of course, the more circular we are on the very end. And we have then integrated these circularity indicators in this at least quite complex spider diagram, normalized to aluminium, and to see that maybe the steel performs same or even better than the aluminium. The carbon fiber plastic has the worst performance, and the wood depends on which of these criteria you're considering. And our key question here, we want to discuss maybe already today and also in future, we want to discuss, is the circularity potential a new and useful new impact category in life cycle assessment? And does it give value added to our assessment? Our Austrian industry partner was very happy about this kind of assessment, because in industry, more and more also circularity is a relevant issue, and they have found indicators where they are really able also to compare the circularity of the different components. So I'm on the end of my presentation. So again, if you have any questions on my presentation, please put them in the chat and we will answer them afterwards. And now I hand over to my colleague in Germany, Jonas Peschke. He will now zoom into a use case for circularity, the example of battery. And Jonas, the floor is yours.
Thank you so much, Gerfried, for the interesting insights and for the brief introduction. Just a short introduction of myself. Again, I have a mechanical engineering background, in addition with business administration. And before I joined the German Aerospace Centre Institute of Vehicle Concepts about 1.5 years ago, I already worked for 6 years in the automotive industry. And as Gerfried already mentioned, one part of the task 52 is the use cases and doing workshops on these use cases of different electric vehicle components. And the starting point of this series of workshops was the workshop on the battery recycling, or the battery and circularity. So as you can see on the first slide, yeah, thank you. the overall goal, as it was the first workshop, the overall goal was to understand current barriers and possible solutions for EV battery system circularity. So to get a broad overview of the current status in the end in the industry. And for orientation, we formulated guiding questions prior to the workshop. They covered different topics like the influence of the design of EV batteries on the impact or the impact on circularity. What are the current activities that the industry is already pursuing, and what barriers are they currently facing? How can circularity be enabled with respect to all stakeholder perspectives, and is further collaboration in the end needed, and how? And the workshop we held took place on the 22nd of May this year, and we had the possibility to combine practical experience from the industry on the one side and results from research institutes on the other side. And as you can see in the right picture, in the picture of the right side of the slide, we had a broad variety of topics covered. We had a look at different R strategies, specifically recycling, reusing, and repairing. And in addition to that, we had insights into boundary conditions of the market and politics, as well as a view on the, of course, important production phase as well of the battery system. So in general, a very broad variety of topics that had to be covered by this workshop. And I would like to give you an overview and our key takeaways on the next slides. For that. On this, I would like to start with the different R approaches that are already being pursued or executed by the industry partners. I would start with the recycling, as it has the highest share in R approaches right now. We had very interesting contributions facing internal recycling and external recycling. And for the internal recycling, we had participants who are who work in the production of aluminium battery housings, and there already the internal recycling is being used. So the production waste is being used in the same production path again, and not only for battery housings, but also for cell materials. Let's say reuse of the production waste is at least planned by contributors we heard in this workshop. Regarding external recycling, so the recycling of the end-of-life product in the end, in regard to that, one of the keywords is the design for circularity. So to already consider end-of-life treatment aspects in the designing phase of the development of the battery system. So in the end, to make it easier to, for example, dismantle the battery in the end-of-life process. So this is a very, this is one of the keywords when it comes to moving towards circularity. Secondly, there are also interesting approaches in different recycling approaches, like the direct recycling, which is an approach based on mechanical processes. They are an alternative approach to the, let's say, conventional ones like pyrometallurgical and hydrometallurgical recycling, for example. And last but not least, there are also already actions ongoing on the automation of certain end-of-life treatment processes. For example, automation of dismantling processes. On the bottom of the slide, you can always see at least some representative questions, barriers, needs that we identified based on the information that was provided in the workshop, and they are just like a part of what can be asked in the end. But just to give you a brief impression of how broad and how big this topic is. So it contains, for the recycling, for example, the question of how can the transport be handled in an efficient way, like the transport of the end-of-life batteries from producers or users to the dismantlers and to the recycling companies, for example. A second point would be the necessity for technical developments in different processes like sorting and dismantling, to ensure higher material, to ensure higher quality and purity for recycled materials, for example. And the third point in our list would be the automation of dismantling processes. So that what we heard in the workshop was that it is still kind of lacking of standardization at certain steps. So, for example, as listed in at the bottom of the slide, there are missing security guidelines right now for the automatization of the processes in the end. The fourth point is somehow related to the second point. So I would say we can go to the next slide and to see the other two R strategies which we covered in the workshop, or which the presentations and the contributions covered. The second one is the reusing. There was an interesting approach, or there is an interesting approach, which we heard of, where the end-of-life batteries are collected through a company internal collection network. And after the collection, the batteries have to be manually tested to their current state, like measuring the state of health, for example. And afterwards, they have to make a decision whether the battery can be reused in a second life, or if it's not possible and therefore it has to be recycled, for example, in the next step. The second life use could be a stationary energy storage, for example, based on buildings, or for grid balancing and so on. As you can see on the right side in the picture, for example, where EV batteries are connected to, let's say, bigger stationary energy storage blocks, and then used in this stationary usage in buildings or grid balancing, for example. The third R strategy we were facing was the repairing strategy. Again, as for the recycling as well, the design for circularity plays a big role, specifically in this part, let's say the design for repairability. So we got first-hand experience in the workshop from a developer of another sector. It was a developer of batteries for e-bikes, and they invented a modular and focused of an easy repairable battery system, in which it is possible to replace broken components easily. Nevertheless, the repairing, of course, cannot be done everywhere, like usually not at home by the user, and also not in every kind of bike shop. So what they told us, they need to certify certain bike shops, which then can do the inspection of the battery and in the end replace the broken battery components. When it comes to automotive sector, we also heard about individual collaborations that are already taking place, where to follow this R approach, but it is, as far as we get the feeling, not as widespread right now. So in the end, we also have this three bullet points we marked as representative for these topics. So it was, for example, how can this testing process, when it comes to the evaluation of the second life of batteries, how can this testing process be improved, especially in regard to the increasing amount of batteries that are coming to the end of life market in the future? Could there be a possibility of data which is maybe provided, for example, by the product pass, or in this case, battery pass? Can this be helpful to somehow make this evaluation process more efficient? Secondly, could the automotive industry in the end benefit through knowledge transfer from collaboration with other sectors like the EV batteries for e-bikes, for example? And as a third point, every company which is involved in the end of life process in the end has to make a strategic decision on which processes in the end should take place in-house and which processes should be covered by external partners. For example, the transport of the end-of-life batteries, or different types of end-of-life treatment, like the recycling when it's not going into second use, for example. Besides the R strategies or the R approaches, on the next slide, you can see the second big topic we covered in this workshop, which contains the boundary conditions for the market and the politics for realizing battery circularity in the end. We had some interesting insights in research on the amount and variety of battery systems, and it showed that, of course, the amount and variety of batteries and battery cell chemistries will increase in the upcoming years, and so because of that, it will be important to consider, besides the end of life process itself, to consider the production or for an holistic approach of circularity. Therefore, we got really interesting insights into the calculation of resulting emissions caused by the production of batteries with different chemistries, and it showed theoretically pretty high potential, of course, to reduce emissions throughout the entire life cycle of the battery in the end, because the production phase is an important phase when it comes to the emissions. Second, the market conditions. Of course, they play a key role, as said, on the way to a more circular economy for EV batteries. We had two different studies shown in the workshop, which were pretty interesting, and where I want to briefly introduce some of the main points and outcomes. So the first study was conducted in Norway. The Norwegian market is a front runner when it comes to adapting EV electric vehicles. And although the extended producer responsibility already exists, it was standard out that the processes between the end-of-life stakeholders, like the producers, or in Norwegian case, importers, and the dismantlers, and, for example, the recyclers, they are still not as well established as they should be to move further towards this circularity approach. To give an example, the dismantlers are still partly facing negative values in their processes, let's say. The processing costs for due to special treatment of these electric vehicle batteries, they are rising, and at the same time, the prices for end-of-life batteries they can sell to, for example, the recycling companies, they were decreasing. And in the end, let's say the end-of-life treatment somehow has to be a valuable step for each of the stakeholders that are involved there. A second study, which was done in the state of Baden-Württemberg in Germany, it indicated the special need for further collaboration, not just between industry, between industrial partners, but also in development between industry and research, to be able to transfer the knowledge to the use in the end, to the practical use. the three key points or follow-up questions and remarks were facing the topic of diversification of battery cell chemistries, for example. How do they affect the processes of the end-of-life stakeholders? Do they have to maybe adapt their processes to certain battery cell chemistries? And how will the increase of the total amount of end-of-life batteries coming into the market be handled in case the market issues that I described earlier will not be solved? So in the end, there is a need for a transparent and established framework, overall framework, that has to consider the perspectives of all stakeholders throughout the entire value chain to make it applicable. Third, what measures can be implemented? And then speaking maybe of political aspects, can be implemented to make the end-of-life treatment of EV batteries in the end beneficial for the stakeholders and to promote this development in the end. On the next slide, to sum everything up of this broad variety of topics on the workshop, I just want to mention again a few points that would try to sum up everything. So the key takeaways from our side would be right now on a very high level. Currently, there are already different individual activities towards circular battery treatment in industry. But there's still room for optimizing on the technical efficiency of the processes for reaching higher quality and purity, for example, of recycled materials. And in addition, the standardization of the processes and to make data availability to know more about the components, specifically in this case the battery in the end. And when it comes to the market conditions, the already mentioned overarching framework, including economic as well as political aspects, has to be established throughout the entire value chain of the battery. So therefore, the collaboration of all stakeholders, not just industry, but also research, have to be included. It has to be promoted somehow, and has to continue that way. And last but not least, just last sentence, as Gerfried already mentioned, there are other components and workshops we are planning. So the next one would be on the 10th of February next year. It has the topic of circularity and traction e-motors, and some advertisement in case there are colleagues who are interested in this workshop, in this topic, and would maybe like to contribute something to the workshop. You are highly welcome to contact either Stefan Schmid or me. Our email addresses are posted at the bottom of the slide. And that's it so far from my side.
Wonderful. Thank you very much, Jonas and Gerfried, for those presentations. We have got a few questions, and the first one, I think, is from Gerhard. He's asking, I think it's for you, Gerfried, if you could elaborate a bit more on why weight has only a minor impact, a minor factor over a lifetime.
I did not get the question. Why what? The first...
Why has it only had a minor impact, is a minor factor over a lifetime?
Yeah, at least in our material balance, we count, of course, the material in the component and all the material that is needed to make it, but also the fossil energy. Yeah, and the fossil energy has also a weight. And that is in the overall mass balance quite relevant, because we are interested to identify the total mass and then assess which mass is circular and which is not circular. And most of the primary energy spent for this component is fossil-based, yeah? And the fossil-based energy is, of course, assessed to be non-circular, and that's why it's so important to have also all the masses involved in the life cycle for the different components.
Thank you. There is one further question. It's from Philip, and he's asking, are there any experiences on addressing the remanufacturing, repair and refurbishment of components? The presented assessment is very material and recycled focused. I don't know if any of you want to jump in there.
Maybe I can start. So in the assessment I presented, of course, we have included in the methodology all the 10R principles. Yeah? So in the methodology, in the calculation of the circularity potential, of course, we can reflect all the 10R principles. And so at least also the remanufacturing, repair and refurbishment of components these are measures to increase circularity. For example, better repairability, you have a longer lifetime, and the lifetime is directly reflected in the utility factor in our assessment. So at least our methodological framework can cover these aspects. In this initial case study I've shown to you, we have not assessed it, but in the upcoming case studies, of course, we will also put a focus on remanufacturing, repairing, refurbishment in addition.
Thank you, Gerfried. I have one further question for Jonas. Can I ask, are there any other R strategies you can think of that might be useful in researching circularity in terms of EV batteries?
So in the workshop, as I said, we covered mainly recycling, reusing, and repairing. Nevertheless, I would say you can somehow also call some activities as no, I'm lacking of the word. Sorry. Refusing is the R strategy I was looking for. I was just thinking about alternative battery cell chemistries, for example. So when it comes to certain raw materials like rare earth elements or so on, or materials that are very valuable, like we could replace, for example, there are chemistries where they replace lithium, for example, via sodium. So there are sodium-ion batteries. They are not that big. They have not that big share right now, but they are theoretically alternatives which could somehow lead to refusing certain materials, for example, in this case. Yeah.
Lovely, thank you. I think we'll take one final question. Well, there's one from Audrey who's asking if she can possibly get access to the various reports and articles that you've presented. Would that be possible?
Yes, of course, because one important activity is to disseminate material. On one hand, we have a web page where you can find all parts of this information. And additionally, you can directly contact us and we can send you the upcoming or the current reports, working papers, documentations we have so far. Yeah.
Wonderful. Excellent. So yeah, we'll send that to Audrey. We'll send that out to you. One final question, I think. Michael has asked, is there anywhere you link to the 18 plus country circularity plans?
Are there any, sorry.
Is there anywhere where you link to the 18 country circularity plans? Is there anywhere you link them?
You link, at least we have collected all these 18 national circularity strategies. So far, they are only available within the TCP collaboration network or within the task. But of course, Michael, of course, can have access. But if anyone else wants to have these reports, they are publicly available. And of course, we can make them accessible to the ones who want to see them. And there's also a more detailed article describing all the analyses we did on these national circularity strategies. So yes, of course, just contact us, please.
Lovely. Thank you very much. That's all our questions today. So I'll hand back to you, Gerfried.
Okay, so we are nearly on the end of this webinar. So I give you a brief outlook and summary of this webinar. One part of the outlook is, as I've mentioned, we are going to do further case studies on assessing the circularity potential. This is a good interaction possibility with different industries, and we will do case studies on the circularity potential for different electric vehicle component, the battery, the e-motor. We will do one on the charger, one on power electronic, one on the vehicle only, and of course on the renewable power plants, especially wind, photovoltaic, and hydro. It's interesting to see that maybe they are not so circular in the overall balance as we think. And of course, very interesting is finally on the overall system, providing a transportation service with battery electric and compare it to conventional activities. So if you are interested to join our activity, please contact me. We are very open. We want to involve as much as possible different stakeholders, experts, and to really have a vivid discussion around these case studies, because they really bring things down to reality and see orders of magnitudes and see the development, and hopefully the good side of our approach to really make circularity measurable and to help really development towards more circularity. Secondly, as Jonas has already mentioned, we have our next workshop on e-motors and circularity. It will take place on February in the afternoon. Of course, I think you are now on our contact list. We will send you an invitation. If you want to present some of your work you're doing in that area, of course, you're highly welcome, because the more external experts that are also contributing to the overall input of the workshop, the more vivid is the discussion. And beside presentations, we also plan an interactive format, an online format, so everything will be online, to have small groups to work on specific aspects on this. So please note in your calendar, February 10 afternoon, further details will be announced. And this is my final slide. What is the key take-home message? We've shown to you that our task, Electric Vehicles and Circularity, has 10 partners in 9 countries. In our task, we've started to develop an initial approach to assess the circularity potential by starting with a definition of circularity in an LCA context, then analyzing the mass balance and assessing the circular and the non-circular flows, or the renewable and the non-renewable material and energy flows. In our first case studies, we also seen that this really ends up with a set of indicators for circularity that also is of high interest for industry to further develop circularity aspects. And very important, energy consumption, type of materials, and lifetime are, of course, essential for circularity, which is maybe type of material and lifetime maybe is quite well known, but also to consider energy consumption, we think, is also a key aspect that has to be reflected in the circularity potential. And these 10R principles, I hope you know now all these 10R principles, which is really the starting point and the most agreed approach to further increase circularity. But in reality, we know by realizing then we are really facing a long list of technical and economic challenges to do so. So the way towards a high circularity is still a long way to go. We're starting to put down some initial conclusions on the very end, just we are discussing them. We see several times already this afternoon that the design phase is very relevant, and in the design phase you can already address all the 10R principles. But very important, maybe not only the design is relevant, we also have to think about new business models to realize circularity, because maybe the responsibility of the product or the service provided needs new business models also, that the design phase really is profitable for the one who's bringing products or services on the market. Maybe a product as a service approach could help out here. Then it's very important to really identify what are the most valuable materials, especially in the European context. We have a strong interest now in keeping critical materials within Europe. So really see what are the value streams that really have to be identified and kept and recycled. And last but not least, we've also seen that information exchange is very relevant, not only in a webinar, also between the different partners in the supply networks. It's not a supply chain, it's really a network, because everything is so much interconnected to each other, and we think this is essential to collaborate, to share information. And maybe the digital product passport, which was also addressed by Jonas this afternoon, maybe this is one way as a platform to collaborate and exchange information. We will have further conclusions. This is the first year of our task 52. And we will come back to you, of course, next year with new webinars. And in the final, after the 3 years, we will have a long list of recommendations to further improve circularity. Finally, I just have to say thank you. Thank you to all of you for joining us, asking us. I especially want to thank Jonas for his contributions, and the colleagues from the UK, Lorraine and Claire. They helped to set up all the technical equipment for this afternoon. They are involved in task 1, which is about information exchange in our collaboration program, and we can very much benefit in our task that they help us to establish such a nice webinar we had this afternoon. So thank you very much for your help and your contribution. And if you have any questions, please send them to us, and we are really happy to interact with you, to exchange with you, and of course hope to see you in our next workshop. Thank you very much and enjoy the rest of the day. Bye-bye.